Our first experiment is the determination of fluid density using the measuring cylinder method. This experiment applies the basic formula for density. Density equal mass divided by volume. By weighing a measuring cylinder before and after adding fluid, we obtain the fluid mass. The volume was measured using the scale on the cylinder. With both values, we calculated density for each fluid. The fluid tested were water, oil, soap water, glucose solution, and salt water. The average density obtained were water 974.44 kg per cubic meter, oil 863.89 km per meter cube, soap water 1025.56, and glucose water 1006.67. Lastly, salt water 998.33 km per meter cube. We observed that fluid with dissolved solutes such as soap, glucose, or salt had higher density compared to pure water. Oil, which has a less compact molecular structure and is nonpolar, had the lowest density. In conclusion, this method clearly demonstrates how the presence of solute increases fluid density and confirms expected density trend across different liquids.
The second experiment used the density bottle method to determine fluid density more precisely. This technique used a density bottle with a non-volume, allowing accurate mass to volume calculation. We first weigh the empty bottle, then fill it with fluid and reweigh it. The difference in mass represents the fluid's mass, and we calculate density using the non-volume. The results were water 1027.67 kg over meter cube, oil 900 kg over meter cube, salt water 1031.33 kg over meter cube, glucose solution 1192.33 kg over meter cube, and salt water 1235.33 kg over meter cube. These results again confirm that fluids containing dissolved substance are denser than pure water or oil. Salt water shows the highest density due to its high solute content, while oil remains the least dense. This method also emphasizes the importance of precision, as trap or air bubble or residual droplets could affect the results. Nevertheless, it provided consistent and reliable outcomes aligned with theoretical expectations.
In the third experiment, we use a hydrometer to determine the specific gravity of the fluids. This method is based on Archimedes' principle, where the hydrometer floats higher in denser fluids and sinks lower in less dense ones. We tested the same 5 fluids and the specific gravity results were water 1.0, oil 0.85, soap water 1.02, glucose solution 1.15, and salt water 1.06. The hydrometer readings confirm that fluids with solutes have higher specific gravities, while oil has a much lower value, indicating that it is significantly less dense than water. This method is widely used in practical fields such as wastewater treatment and chemical mixing, where knowing the relative density of fluids is crucial. It also reinforces fluid behavior principles such as buoyancy, flow resistance, and pressure head.
The fourth experiment focused on determining the viscosity of the fluids using the falling sphere method, which is based on Stokes' law. A marble was dropped into a measuring cylinder filled with each fluid. Once the marble reached terminal velocity, we measured the time it took to travel a set vertical distance of 10 centimeters. The results were water 0.5 seconds, oil 1.20 seconds, soap water 0.58 seconds, salt water 0.62 seconds, glucose solution 2.35 seconds. From these times, we observed that glucose solution had the highest viscosity, resisting motion the most, while water had the lowest. Oil, although less dense, still had a relatively higher viscosity than water due to the molecular cohesion. This experiment highlighted how viscosity influences fluid flow, energy loss, and system efficiency, important in pipe design, pump selection, and industrial fluid transport.